Maybe I can just start talking. So I'm supposed to talk about 2D crystallization through dialysis. And it's a really topic I don't like to talk about at all, and I think that's why Henning likes me to talk about it. And it's really, all of you have done this, and so probably all of you have experience, and think what I'm really trying to do is that you actually start to discuss with us. So that this is not just me talking, but I'm really going to try especially to get Andreas Engel to talk about, because he's really a specialist in this. And he's a physicist, so he thinks he can actually really well define how to make 2D crystals. I'm a biologist, I really don't think you can ever define it in any way. So hopefully this becomes an interesting discussion, and at some point slides would be really great. Because my first slide is great. So my first slide, I'm really trying to get you into discussion, and one way to do this is to really provoke people. And so my view of 2D crystallization is it's really kind of voodoo. You can never predict what is going to work and what is not going to work. And so I come out of Andreas Engel's lab, and at that time I had certain views of how to make 2D crystals. And then as I started my own lab, my views changed, and now I have kind of different views how to make 2D crystals than I used to have. And I think that's true for everybody who starts his own group and starts to make 2D crystals. Your belief system really changes. And so it really depends on the lab and the PI what you believe will give 2D crystals and what is not going to make 2D crystals. And so another problem with 2D crystallization is it's kind of an anecdotal science. So it's a lot of people talking to each other and getting some information and saying, oh, this worked, and so we start to believe that this is actually working. And then other people think something else works. And so it's really kind of a strange science. It's not, and one of the problems why this is the case is because we only describe and report successful experiments. So we do hundreds of trials, and 1% works, and these 1% is what we really report in the papers. And so there's a good chance that all of us actually make the same mistakes over and over and over again, because we just simply don't know that other people have done these mistakes before. And so one problem with the publication system is that we can only publish positive results, while I think we could actually learn a lot from all the things that don't work. And I think Andreas is a very good example, because he very often actually says what is not working, and we should try and do this more often. And so one of the problems is that 2D crystallization is very easy in principle. So you start with your solubilized protein, you add a few lipid molecules, and then what you try to do is to basically get these mixed micelles, where you have the membrane protein surrounded by the lipid molecules, and the whole thing solubilized by a detergent micelle. And once you have that, you remove the detergent, and there are different ways to do that. So my talk is about dialysis, but there are different ways which you will hear about. And then, if everything goes well, we get an artificial lipid bilayer with regularly arranged proteins, a 2D crystal. So the principle is really trivial, but in practice, none of this is really trivial. And so I don't even know how to think about how a 2D crystal actually forms, but for me, the most fruitful way to think about it is that it's a two-step process, which is almost certainly wrong. But basically, the way I think about it is that we first basically reconstitute the protein into a lipid bilayer, which still has kind of detergents incorporated. And so these micelles then interact, and you get another protein into this lipid bilayer. And so you get reconstitution of the protein, and then as you continue your dialysis, you basically get an ordering of the protein in the lipid bilayer. So that's the way I think about it. But it's almost certainly not correct, because very often you can actually have the protein go direct into a crystal without a reordering. Or you can actually form membranes first and then incorporate the protein into the preformed membrane. So how 2D crystallization really works is kind of elusive to me. And do you agree with this? Or?
Right. I mean, this is a picture we usually draw. Perfectly correct. But already the first step is a very big question.
Yeah.
How are you sure that when you have your protein completely delipidated, you will get back lipids onto the protein? And most of bad cases are when your lipid goes its own way, maybe
So this is the next way. So the first slide is the kind of way that I look about it. And then one way that I learned to look about this is from Andreas' lab is basically you have three components that interact with each other. You have the protein solubilized in detergent, you add detergent solubilized lipid in some kind of buffer, and then you remove the detergent and you try to get 2D crystals. So what is kind of important, one way to look at this is the interactions between the protein, the lipid, the protein detergent, the lipid and detergent. And so what Andreas just said is if you have different interactions of the protein with the detergent than the lipid with the detergent, you can have different things happening. So for example, if the protein detergent interaction is much stronger than the lipid detergent interaction, what happens is that you remove all the detergent from the lipid, you get nice empty vesicles, the protein is still with detergent, then you remove the detergent from the protein and you get nice aggregates. So this is a problem, obviously. You can also have the opposite situation where the protein detergent interaction is much weaker than the lipid detergent interaction. And so you first remove all the detergent from the protein, you get protein aggregates, then you remove detergent from the lipid, and you get nice large empty vesicles. So obviously this is also not working very well. So what you would like to have is a protein detergent interaction similar to the lipid detergent interaction, so that you remove the detergent approximately at the same time for the two components, and then you really reconstitute the protein to the lipid membrane. So I spent a long time thinking about reconstitution in these terms, but then if we really believe that the mixed micelle is the intermediate form for the 2D crystallization, then all this really doesn't make any sense anymore because you actually need the lipid to interact with the protein and the whole thing being solubilized by a detergent micelle. So I have a very hard time coming up with an idea how to think about the whole problem. And so what I think is a good way to think about it is just look at all the individual components and think what we need to think about for each of them. And so the protein is obviously a given. That's what we're interested in. We want to get the protein structure. But there are a few things we can think about. So first of all, we need a very pure and homogeneous protein. And homogeneity is not only that we have a pure protein, but a protein can also have different oligomeric states and different functional states. And so what we ideally want is a protein that has one particular functional state and one particular oligomeric state. And that should give the best 2D crystals. But this is what I learned as I grow older. None of these rules really are fixed. Because there are, when you look on a gel, there are oligomeric states, there are mixtures, and you can still get a nice 2D crystal. And presumably what happens in this case is that you have a dynamic equilibrium between different oligomeric states. You start to crystallize one particular oligomeric state, and that will drive the equilibrium into the state, and then you end up getting a nice 2D crystal, even though in solution you actually have a mixture of different oligomeric states. And probably the same is happening with functional states. So I do believe to start with, you want to have the most homogeneous protein, but it doesn't necessarily mean that if you have a heterogeneous population that you don't get 2D crystals. So one nice thing is you can actually use EM, you use negative stain EM to just look at your protein, and you can actually see how homogeneous it is. So this is something we electron microscopists have really an advantage that we can look at the purified protein and see whether it looks good. If you have a lot of aggregates, we don't even go and try to make 2D crystals. Another thing is, if you have actually a mixture of proteins, what can happen is that you can still get 2D crystals because the proteins can actually segregate in the membrane, and I've seen this with my own proteins, that you actually can have a nice tetragonal crystal on one side, and within the same membrane you have a hexagonal crystal right next to it. That can work, but most of the cases, if you have two proteins, they're going to mess each other up and you're not going to get good crystals. So another kind of thing that I do believe in as a general rule is that higher oligomers will give you better 2D crystals. And the reason is quite simple, because if you have a higher oligomer, for example a tetramer, you have a certain shape to your oligomer. And so this is kind of the self-assembly idea. If you have a nice square, the nice square will much easier make tetragonal crystals than hexagonal crystals, so you already have kind of a building block to define your 2D crystals. So this is one of the few rules I actually believe in. So if you have an equilibrium, a dynamic equilibrium between oligomers, it's always better to try and drive it into the higher oligomeric state than trying to go to the monomeric state. So have people any kind of experience with these kind of oligomeric mixtures? No? Anyway, you?
I think many of us looking at that, and would agree, yeah.
Okay, good. And then there's another.
Do you have just an example?
Personally, I actually don't have an example. So I actually always believe that you have to have, so as I get older, my beliefs change all the time. I did believe you have to have one state. And actually, Werner's lab has a lot of cases where he has different oligomeric states and he still gets nice 2D crystals. So that's actually what changed my opinion. It's not my personal experience.
In most cases, oligomers are also related to the function of the protein. So when there are lower oligomers than the tetramers, for example, the protein is less stable. So it's difficult to compare. An unstable protein, monomer.
Now, if you have obligate oligomers, then obviously if you don't have the oligomer, you're dead. But there are proteins that can actually make, so MP20, one of the, well, I do have an example, actually. We work with MP20, and that makes actually all kinds of different oligomers as part of the function. And still we get 2D crystals which have only tetramers. So I forgot about that, yeah. So. Photosystem 2, yeah.
Yeah,
So
that's the example that I mentioned. Photosystem 2, if you remove the phosphatidyl glycol, the monomer is unstable. Yeah, but also there's high order arrays as well. There's functional implications for having more than one dimer, for having macromolecular array, which is what Tom's.
But my basic view is that while I used to throw everything away which was not nice one oligomeric state and would say that it was never crystallized, it's still worth to try actually make 2D crystals because it does crystallize. So
what about the situation where you've got an oligomer that doesn't have crystals? Say you've got a sevenfold oligomer or something like that.
what?
A sevenfold symmetric oligomer or something.
Which is not very frequent in biology. But
Fivefold, that's not going, or fivefold, that's not going to fit into a crystal lattice. Do you think that would be more or less likely to obey this rule than something that's, say, fourfold symmetry?
No, I think the fourfold symmetry or threefold symmetry, sixfold, these are the strong ones. Fivefold symmetry is probably not as strong because you would have to have different interactions. So you would probably have a P1 crystal in the end anyway. So I think, Kenny?
I just wonder, how do you identify
Either by EM or by native blue, gel electrophoresis, or just SDS page. And that's another thing. If it's an oligomeric mixture in SDS page, it doesn't necessarily have to be an oligomeric mixture in the EM. So we actually very often look in the microscope at our proteins before we start to make 2D crystals. It's a very easy and very informative way to start your experiments.
How many states we're talking about? Two or multiple?
So yeah.
How many states we're talking about?
So if you have a mixture, MP20 is a mixture between monomers, dimers, tetramers, and octamers. And some of them are probably more prone to crystallize, and then the dynamic equilibrium goes into that state, and that crystallizes.
So, a lot of times we have the problem like the protein becomes oligomeric with aggregate.
Yeah, then you have a problem, I agree. I don't know how to respond to that. If you have a pure tetramer, so you should actually have a nice seed to make 2D crystals. Why it then starts to aggregate is actually not very obvious to me. So each protein is different, so you will run into different problems with every protein. But as a basic rule, I think having an oligomeric state. Yes? It has a kind of a building block shape. So if you have a tetramer, it's very likely that you make one tetramer next to the other, and you're not going to make a trigonal crystal.
I agree on that, but I think one main reason why high oligomeric states are probably also very is they stabilize permanently. It is known that most of the structural oligomeric proteins are just oligomeric for like proteins.
Okay.
It's not needed for function, it's needed for stabilization. One example is AHA. If you cut out the beta sheet, it's monomerize it,
I see.
I'm not sure if the crystals have been tried with better
No, I mean, I agree with that, but if you have a dimerization domain in your protein, the protein wants to be a dimer. If you cut it off, I mean, then you make an artificial system. So, but I do agree, if this is the case, whatever stabilizes the protein is obviously better. So, yeah.
Just a comment with regard to the previous question. Clearly, this idea of oligomers leading to crystals is only going to work if the oligomerization is carried through the transmembrane spaces, or in that plane, if the oligomerization is occurring in the plane of crystallization. So
in the plane of crystallization, which you don't know whether it's in the membrane or outside of the membrane. So you can make 2D crystals either through soluble interactions or through transmembrane interactions.
Yeah, but not like if the aggregation that you were talking about is stacking, for example, specific stacking or something like that, then maybe that's why there's a problem.
Yeah. So you can see a lot of people have different views, and what is really important is to discuss and see whether we come up with a consensus or not. And so another of these kind of controversial issues is if you want to keep the tag that you use for purifying a protein on the protein, or whether you want to cut it off. If you keep it, you have more solubility of your protein. It's easier to keep it in solution, but there might be actually interference of the tag with the crystal formation. And I think the answer to that is you try both. You try to make 2D crystals with and without the tag and see whatever works better. And so one important thing that came up really is that every homologue of a protein seems to behave differently. So something that is now very common in X-ray crystallography is you try many different homologues and you just see which one is going to work best for you. And so I think that is also true actually for 2D. And so expressing more proteins is probably a better idea. So the detergent, as you heard,
How much does it need to be delipidated?
What?
Oh, that will come. Oh, dilipidation.
I don't think this will come. I mean, this is a good question. And dilipidation really. So yeah, detergent dilipidation. So how much should the protein be dilipidated? If the protein actually survives complete dilipidation, that I think is the best thing to do, because then you can really very precisely get the lipid to protein ratio artificially by how much lipid you add. But it depends obviously if the protein dies, if you remove the lipid, you have to keep it. And so that becomes very tricky. This is the part of choosing the detergent, which detergent actually suits your protein the best. And so I think I'm actually going to talk about this, but the detergent in these three systems, so the protein is what you're interested in, and the detergent is pretty much defined by what the protein likes and what it doesn't like. So there's not much freedom, in my view, playing around with detergent. And so what a detergent obviously has to do is has to try to solubilize the protein out of the membrane, and then once it's out of the membrane, it has to try to keep it stable in solution. And so, as Michael already mentioned, in my view, the solubilization efficiency is really not that important. If you can extract only a small amount of protein, but it's happy and it's functional and it's structurally intact, and that's what you need. It doesn't really make sense to try and solubilize a huge amount of protein out of the membrane. All of it is completely denatured and inactive. So it's really the protein that defines which detergent you're going to use. And then again, there's always trade-offs. So we like obviously high CMC detergents because we want to dialyze it away. But high CMC detergent, as a rule of thumb, are more aggressive than the low CMC detergents. And so if you can, you're happy if you can get away with a high CMC detergent. If you can't, you have to use a low CMC detergent. And then sometimes dialysis can take weeks. And so while this is inconvenient, it's actually not necessarily a bad thing if you have to wait for a long time for reconstitution, because that gives it more time to actually form crystals in the membrane. And if you're too impatient to wait this long, you can use other methods like detergent chelation and biobeads. One thing you should keep in mind is that in 2D crystallization, the detergent actually has to keep the protein stable for much shorter time than, for example, in X-ray crystallography, where crystal growth can take several weeks to months. In our case, the detergent only has to keep the protein stable from the time you take it out of the membrane until you add lipids back, not even to reconstitute it, just add the lipid back, because then you get mixed micelles, and that will already stabilize your protein much more. So we can actually get away with harsher detergents than extra crystallographer, and that might be an advantage as we have.
Well, I
disagree. Good.
would actually disagree here, because
You would like to do
I
this.
including my own apartment. But you have crystals, and you have crystals for 1 year, and for 3 years, and for 5 years, and well, where's the structure, the 2-angstrom structure? Well, and I think the reason that we don't get there is that we think we can get 2D crystals from a crappy purification, and the crappy is more or less happy, and so at least it makes some crystals that are okay, negative stain. But if you want a 3-angstrom crystal, well, some group can do that. But in most cases, including my own lab, I think this is one of the reasons why we don't get to the very high resolution crystals, because we think we don't need X-ray quality. And I think the cases where you get the excellent crystals, that was often the case when you had X-ray quality to start with. So I think we should try to find a purification that is as perfect as you will need for 3D crystals, and then try to go for 2D crystals, and you have a better chance of going to the very high resolution data in the end. So, all is nothing.
Can I rebut? I'm just shut up and go move on. No, I mean, I agree with that statement. You always want to have the very best detergent that you can have. But we might be able to get at least intermediate resolution structures with proteins that are not very stable in detergents, because we can stabilize it for short enough periods that we can get 2D crystals. And you might never get 3D crystals with those kind of proteins. But basically, I agree, the best detergent, the most stable the protein in the detergent, this is the best detergent you can choose. And then, so one of my beliefs was that use of detergent mixture is complete nonsense. It's another one of my beliefs that are changing. And so, for example, Michael's example that you add detergent. So I never understand. I always try to think about it. And so you have a low and a high CMC detergent. So what happens if you start to dialyze, you first get rid of all the high CMC detergent because it disappears, and you're left with the high CMC detergent. So the other way around, whatever. But basically, the high CMC detergent has disappeared by the time you get to the CMC of the low CMC detergent. So what's the point of having the high CMC detergent in there to begin with? So I can't rationalize it, but obviously it does make a difference, as Mohamed has shown. So how do you rationalize something like that, Michael?
Well, I was just going to say, I think to assume that there's no detergent molecule in a 2D crystal might be incorrect. I think in some cases it might be the case that the detergent, that in the same way that lipid molecules can aid 2D crystallization, a single detergent molecule might aid that as well. And you don't actually remove all the detergent, so maybe that's why you see the sort of effect.
But which detergent would you assume would end up in the 2D crystal, the high or the low CMC detergent?
The one that's bound most tightly is not necessarily dependent on the CMC.
That sounds reasonable.
I'm kind of thinking reasonably theoretically here.
I mean, this is what we're trying to do, to think theoretically about what is happening. Well, so that sounds like a good explanation. Okay, so in any case, it seems to matter if you have a detergent mixture, which I could never understand before, but this sounds like a good explanation why it's actually good to have mixtures. And then another thing where I changed my opinion, again, the initial detergent concentration, what does it matter? Because everything starts when you reach the CMC. So then you start to get reconstitution, that's when you get crystals. So why do you care whether you initially have a high detergent concentration or not? Because it doesn't matter as long as you're above the CMC. So I never understood the point of trying to regulate how much detergent you have, but it seems to make a difference, and I think you started this detergent protein interaction by NMR, and somehow the detergent concentration actually has an influence on the protein structure.
That's correct. The NMR field uses primarily phospholins because they don't have the issues of crystallization. Phospholins can work very well there, and they have a very nice way of determining detergent concentration against an absolute scale, like gradient calibration. They can actually tell how much detergent is in there, and they see that as you increase the concentration of detergents, you can watch your fold or the chemical shifts change. You get broad spectrum.
But the question that
Undergoing conformation changes, instability.
But the major question is, if you go back down in the concentration, do you come back to the initial protein conformation?
So the idea that, yes, I think the answer is yes. You can,
so if this is true, then why does it matter if you start with a high detergent concentration or not?
It's a little bit a question. You know, it's a race against time. Your protein can sustain high concentration of detergent for a certain while. So when you have a lot of detergent, you take a long time to get rid of it.
No, but that's...
I think the protein, this is a little bit what you alluded to, it starts to change at a high concentration. As you pull it, as you pull the detergent away, the protein is already half dead. And it cannot switch back into its native concentration.
But if we believe in the idea of these mixed micelles, the moment you actually add lipids to your protein, you have already lipids stabilizing your protein, so then why does it matter if you have a high...
This is really the sore point. No, exactly true. We always were dreaming about experiments where you say, I have a lipidated protein, I have my detergent lipid micelle, I throw things together, leave it overnight. This is what we did all the time.
Mm-hmm.
And then we have this magic thing that we reconstitute the lipid ring.
Mm-hmm.
And if you don't have this, then of course it's a problem. And this is where I think it is not always ideal to have a very high concentration to keep things soluble, because you mess up your protein in an irreversible way.
Mm.
I mean, this is perhaps the best explanation to keep the initial detergent concentration very small.
Okay. So if you can, you obviously want to keep the detergent concentration small, but the problem is very often once you purify protein, you have to concentrate it, you concentrate the detergent, and then we need a drop box. Okay, the next thing is the lipid. And of all these components, the lipid is really the one that you can freely choose. And the question here, however, is how important is actually the lipid to make 2D crystals? And I think it depends really on the protein. So for aquaporin, you can make 2D crystals with all kinds of different lipids. Other proteins have a much more specialized need for certain lipids. And once again, I'm not sure whether these specialized lipids you just need to really stabilize the structure of the protein, and then the remaining lipids are actually not that important anymore. So once again, it's kind of I'm not so sure how important the lipid really is to get 2D crystals. And then this is something that I mentioned before, the phase transition temperature. So we always think that we have to have a low phase transition temperature lipid to make good 2D crystals. But I actually still don't quite agree with that. So again, if you believe in the concept of the mixed micelle, if it exists, you actually already disturb the structure of the lipid, so you will have no chance of actually have crystalline lipids. So in this case, the phase transition of the lipid really doesn't matter. If you don't have mixed micelles, then obviously it matters. But once again, we don't really know what's happening at this point. And so one of my thought points about 2D crystals, something that I find extremely frustrating, is the extremely poor reproducibility of 2D crystals. And we don't really know why it's so poorly reproducible. And one of the things that I believe in is to try to make everything as reproducible as we possibly can. And so there's, for example, the question, the lipid stock solution. Do you make a lipid stock solution and then use the same stock solution all over again to make the 2D crystals again and again and again? Or do you make the lipid fresh every time you make new 2D crystals? And the problem is, if you keep the lipids in stock solution, you have the problem with lipid oxidation, especially if you have unsaturated lipids. So for the lipid, to get high quality lipids, it's better to make a new stock solution every time you make 2D crystals. But in my view, the reproducibility is probably better if you keep the same stock solution over and over again. So all of you probably have made 2D crystals. Who is making lipids fresh every time? Hands up. Okay. Who uses a stock solution? Who gets reproducible crystals? Who doesn't get reproducible? There's no clear correlation.
I would like to tell a story from Vincent's lab. They have nice crystals and then try to reproduce them with a new batch of lipids. I think they got them as powder and formed it in chloroform and put the chloroform lipids into glass vials with a
So when do you stop?
and stored it at -20 and
Am I really over?
again. And the solution in the end was that the chloroform dissolved the glue of the rubber in the cap. And the glue went
So how much time do I have?
melted up forever.
It's over. Oh.
And then when they found that out, they had to throw away all the lipids and buy new ones, and they had the crystals back. So I think the question is also, how do you store the shock solution? In water, or in chloroform, or as powder, or powder not?
Anyway, there are lots of these kind of questions, which are really trivial questions, but they have a huge influence. And so so my time is over. But I hope you have, so all these slides, I have a lot of more slides, and you can read them on the internet. But I think it's important to have these kind of meetings to discuss experience and to actually try and come up with some principles, what is really important and what isn't. Yeah.
Because often the time we assume that our protein lipid nitrogen mixture is in equilibrium to start with.
Mm-hmm.
How do you judge it?
How do I what?
How do we say, most of people do say, if you keep it overnight, it should have happened.
Yeah, so this is again one of these belief systems which you believe, I happen not to believe, now I might believe it, I don't know. So if once you make your mixture, do you actually keep it overnight and pre-equilibrate it and then you start your dialysis, or do you mix it and then start the dialysis immediately? My view again is that once you mix it and you start to dialyze, it will take quite a while to get to the CMC anyway, so it has a lot of time to pre-equilibrate anyway. But some people will swear to the fact that you have to pre-equilibrate overnight before you dialyze. And so once again, I don't have a rationale for that, but there might be reasons for that. So I apologize, this is my time, but the idea is we are here now for a week and we can discuss all between us what you think is important and what isn't. And so that's it.